In the previous video, we focused on defining what a fertiliser was and the elements that are often contained within fertilisers, so nitrogen, phosphorus and potassium. And we paid particular attention to nitrogen because it's probably the most important element out of the ones that we've looked at in fertilisers so far. And to make sure that we're putting nitrogen into the soil, we mentioned that we use compounds such as ammonia or nitric acid to do that. And there's two key processes at National 5 level that we need to know about that will enable us to actually produce these compounds from gases in the air. So we're going to focus on both of them in this video. So first of all, we're going to talk about producing ammonia and the process that's used to produce ammonia called the Haber process or the Haber process. So chemists began to look at ways of producing artificial fertilizers containing nitrogen compounds. And although nitrogen was the obvious starting point because there's lots of nitrogen in the air, chemists actually had huge difficulty in getting it to react. Now, the breakthrough came in 1904 when a German chemist, Fritz Haber, found a way of basically turning the nitrogen and hydrogen, gases that are found in the air, into ammonia. And that manufacture, that commercial process, is still used today, and it's called the Haber process. And essentially what happens is nitrogen and hydrogen from the air react to form ammonia gas. Now, there's a few key points that we need to discuss about this reaction. So firstly, this is not balanced. This is not a correct chemical equation because there are not the same number of atoms on the left as there are on the right-hand side. So we're going to fix that first of all. So you'll notice we have two nitrogens on the left, but only one on the right. That is not good enough. We're going to have to multiply that entire compound by 2, so 2 ammonia molecules. So now the nitrogens are balanced. However, we now have 6 hydrogens in total on the right-hand side because there's 3 originally, and now that's been times by 2. And we only have 2 on the left, so we're going to have to multiply that 2 by 3 to make sure we have 6 hydrogens on both sides. So now that this equation is balanced, we can discuss what actually happens in this reaction. So the other thing you'll notice is it's not a normal reaction pathway arrow that I've used. It's a sort of double-sided going left and right arrow thing that I've used, and this is to note that it's a reversible reaction. So whilst we are trying to make ammonia from nitrogen and hydrogen, just because of the specific chemistry that goes on in that reaction in terms of the bonds that are being broken and formed, some of the ammonia actually wants to turn itself back into nitrogen and hydrogen gas. So we have to carefully construct a reaction environment, a set of criteria, a set of reaction conditions that will enable us to get as much ammonia out of these two gases as possible. And there's a few ways that we do that. So first of all, the reaction is conducted at 500 degrees C. It's also conducted at 200 atmospheres, which is shortened to ATM here. And an ion catalyst is used as well. So because it's not possible to convert all of the hydrogen and nitrogen into ammonia, we try and get as much of it into ammonia as possible without losing any of it back to the original gases. So the way that we discuss that is in terms of improving the yield. So the yield is what we get out of the reaction. And there's a few kind of key points that we can take from these conditions that will enable us to improve that yield. So first of all, high pressure is used. And the high pressure, really this is a higher and advanced higher concept, but for just now, know that it wants to go to the right in terms of the equation if we use high pressure because of the type of reaction that it is. What we can also say is that moderately high temperature is used. So in order to improve the yield, we have to consider what happens at either end of the temperature scale. So in simple terms, at this level, we want to know that at low temperatures, the forward reaction is basically too slow to be economical. So thinking back to rates of reactions, we know that generally speaking, if we increase the temperature of a reaction, there will be more particles that have enough kinetic energy to collide successfully and that they will react to produce a product. However, if the temperature is increased too high, because of the type of reaction it is, right, even though the rate will increase, as temperature increases too high, the backward reaction becomes more dominant, it becomes more favourable because of the type of reaction. that we have going on here. So whilst we don't want the temperatures to be too low, because then there's no point in doing it, it'll be too slow that we'd actually be wasting money for the amount of material we're using because of how expensive it is to run conditions like this. But we don't want the temperature to be too high, because then it's going to start wanting to go to this backwards reversible reaction. So we have to have it somewhere in the middle. And for this reaction, that's where 500 degrees Celsius is. Now the last point to mention is, of course, we're using an iron catalyst, and that will increase the rate of reaction, because thinking back to that topic again, when we use a catalyst, it provides an easier pathway for the reaction to happen, and in some cases will make reactions happen that would take potentially years to happen in a few hours. So catalysts can be a really powerful way of increasing our yield and making sure that we get the most out of our reactants that we are using. So our key points so far: in the Haber process, which is used to produce ammonia, we use a high pressure environment, we use relatively high temperature, and we use an iron catalyst to produce ammonia from nitrogen gas and hydrogen gas. And I should also mention at this point that unreacted gases, because we can't get 100% of our reactants to react all the time, before the gases are cooled and the ammonia is collected as a liquid, we will have our unreacted gases being recycled back, actually taken out of the reaction vessel that produces the product, and put back in with the reactants to try and use them again and try and get as much product as we can. So this process is still used today. This is, by the most part, how we still make ammonia commercially, how we still manufacture ammonia. And the second compound we're interested in looking at today is nitric acid. And the process that we use to make that is called the Ostwald process. So, nitric acid is again used to make nitrate fertilizers, for example, like potassium nitrate and ammonium nitrate, which we've already looked at. And it can be made by taking nitrogen dioxide produced in lightning storms and in car engines due to the spark plug, which ignites gases present in the air. And we then have to consider, well, how do we make nitrogen dioxide? We take nitrogen molecules and we react them with oxygen molecules. And this actually requires quite a large quantity of energy. So like I mentioned, naturally this happens in things like lightning storms. So that's because of the very strong bonds that are between the nitrogen atoms. But we have our nitrogen and oxygen, if we think about exactly what happens from the very beginning, and they form this nitrogen dioxide. For this reaction at National 5, we don't have to know the specific chemical equations, but I've written in the formula anyway. And then, as I mentioned, that all-important nitrogen dioxide is then basically reacted with more oxygen and some water, and that is how we form our nitric acid. And although this method, as I mentioned, for making nitric acid is very expensive because of the large amounts of electricity required to make the nitrogen and oxygen react in this first step to break these strong nitrogen bonds, it's still popular because these methods are very difficult to come up with, right? It's very difficult to find ways of making relatively complicated molecules from very, very simple molecules. And we're still working on that today. But again, to increase the yield, we want to think about things that we did in the Haber process and how we might do something similar in the Ostwald process. So again, we want to think about moderately high temperature. Again, this is a similar type of reaction, and we'll go into further detail at why this is the case at a higher level, but for just now, remember that if the temperature is too low, then the reaction won't proceed at a rate that is worth spending the money on, because we won't get enough to make enough money. But if it's too high, it will push the reaction back the way. So we want a moderately high temperature. And then again, it's very important to use a catalyst to make sure that this reaction is going as fast as it possibly can. So as well as remembering that that catalyst is used and it's again a moderately, relatively high temperature, it's important for these reactions that you don't have to remember the specific chemical formula, or certainly not balancing any chemical equations, but you do have to remember the elements that we use to produce each step. So for example, you should be able to at least work out, well, to produce the nitrogen dioxide, what chemicals will I be using? Or if you are asked, for example, if these chemicals were going to be used as starting reactants, what is the product that you would end up with? And of course it's nitric acid. So remembering the name of the process, the compounds that are involved at certain steps, and the conditions for these reactions, Ostwald and Haber processes, is what you need to know for this part of this topic.